Welcome to the Crazy Hat Chemist. So another video in bonding and molecular structure. So let's get moving. Bam! So today we're going to do xenon difluoride's molecular geometry and oh, so much more. So xenon difluoride. Yes, I know that xenon is a noble gas. But if you look there, xenon is relatively down and it does interact with other elements, but this is just looking at things and see how they work, okay, in terms of molecular geometry, just examples. So, xenon difluoride. There's the formula. You're going to look at your periodic table and determine the number of valence electrons in xenon. That's 8. Fluorine, that's 7 times 2. We're going to add these numbers up. We're going to get 22. We're going to divide this by 2, and then bam, we're going to get 11 pairs of electrons. The least electronegative element goes in the middle, and of course, that is xenon, because it can't be the fluorine, because that's the most electronegative element. So the xenon goes in the middle. Then the fluorines go around it like thus. Okay, you can put them up and down. You can put one up and to the side, one up and to the side, down and to the side, down and to the side, 90 degrees apart. It really doesn't matter. Okay, you're going to get the same Lewis dot structure. Okay, now what we're going to do is we're going to place pairs of electrons in between the central element and the outside element as sigma or single bonding pairs of electrons. Then we have electrons left over, so we're going to place those pairs of electrons on the outside elements like this. Okay, now you should see that the fluorines have an octet, but yet we still have excess number of electrons. We have 3 pairs of excess electrons, so we're going to place those on the central element like this right there. And xenon is greater than period 3. It's period 3, 4, 5, and 6. It can exceed the octet rule and be hypervalent. And xenon is one of those. Fluorine is period 2, must obey the octet rule. Now what we're going to do is we're going to clean this baby up. We're going to draw lines for bonding pairs of electrons and keep those dots as lone pairs of electrons, either on the central element or on the outside element. It really doesn't matter. And this is what we should get for the Lewis dot structure. There's that xenon in the middle. You have 2 bonding pairs and 3 sets of lone pairs on the central element there. Okay, we're going to get that axe-like structure. That's A for the xenon in the middle, X for the 2 fluorines on the outside, so that's AX2. And then there's 3 sets of lone pairs of electrons on the central element. That's an E3. So that's A, X, 2, E3. That is 2 bonding and 3 non-bonding pairs on the central element. From this, we should be able to get the shape of this. Now, again, you have memorized shape names, molecular geometry shape names with either the AXE structure, okay, or the bonding and non-bonding type of structure on the central region. And from that, you should get that this is linear. And what are the bond angles for linear? This is a no-brainer. That's a 180 degrees. Now we're going to get the hybridization of this, and we're counting the number of domains around the central region. Whether they are bonding domains or non-bonding domains, we're just counting the domains around the central region. Let's count them. That's S, P1, P2, P3, D. Bam! That's sp3d hybridized. Now what we're going to do is get the polarity of this. Now before we do that, put this mouse down here. I'm going to show you the molecule here. Okay, there are 5 domains around it. Okay, the xenon in the middle is the purple thing, and the green things right here that I'm holding on to, those are the fluorines. These tan colored things here, these are the lone pairs of electrons on the central region. It's a trigonal bipyramidal structure of electron domains around the central element, but the number of bonding domains, I'm holding on to them, are only 2. Bonding domains, okay? So this is obviously linear. The xenon and the 2 fluorines are obviously linear, and that's why we get the 180. Now, is there a difference in electronegativity right here? So do you have polar bonds? The answer is most certainly yes. Okay, now is the molecule symmetrical or asymmetrical then, is the case. So is it symmetrical or asymmetrical? It is symmetrical. So because it has polar bonds and it is symmetrical, both of those things need to qualify as these electron domains as far as the difference in electronegativity. Okay, you need to have polar bonds and asymmetry. So polar bonds and asymmetry in order for it to be polar. So even if one of those doesn't work, then it's nonpolar. Okay, so this is a nonpolar molecule. So it's very unusual to have lone pairs of electrons in the central region and having it be nonpolar. But this is a perfect example of that. So that's why this is symmetrical and nonpolar, or rather, it's nonpolar and symmetrical. Okay? All right. Fantastic. That was another great video. Okay? And a great hat. Only you can prevent forest fires. Give me a thumbs up if you like that video. Subscribe to my YouTube channel and be here. Be square. Smokey the Bandit.